When we think about materials, we often imagine them as perfectly symmetric, with atoms arranged in neat, orderly patterns.
In reality, everything is moving and the atoms are dynamic. We can also have imperfections, where some of these atoms would be missing, and that would influence a lot the properties of a material. And that's very important to understand that if you want to find new, better materials for applications in solar cells, for example. The long-term goal of my research is to develop realistic models, which we can use to study materials, and then find those that are better for solar cells or other semiconductor devices. And we can make them cheaper, more efficient, more stable.
Most solar cells today rely on silicon to convert sunlight into electricity. But there are other materials that might do this job more efficiently. A promising candidate is a group of materials called perovskites.
Halide perovskites are an exciting class of materials that were interesting in the area of solar cells. First of all, they are quite complex, so there is so much physics, so much chemistry, so much material science to be discovered in them, and we have many questions that are interesting for scientists.
One challenge with perovskites is making them more stable. Improving their stability often means creating and testing many different perovskite structures in the lab, but this is very time-consuming. Julia Wiktor and her team are paving the way for a faster way to discover new materials. Using supercomputers and AI, they create digital models of perovskites and other materials that replicate their real-world behavior, down to the smallest atom. These models enable researchers to perform digital experiments on thousands of materials, dramatically speeding up the process.
I think that it's very interesting to model materials because we don't even have to see the material or make it to predict how it will behave. And if we make just computer models, we can make many different structures and then test them and see which ones are promising, and then maybe we make only those in a lab.
These computer models are based on the laws of physics and quantum mechanics. By running simulations, researchers can understand how atoms and electrons interact within a material and determine its properties, such as its ability to absorb solar energy. However, many computer models are too idealized. They don't fully capture how materials behave in real life. This is the challenge that Julia Wiktor and her team are working to solve.
I think what is unique in my group is that we really try to push the models to be more realistic. We want to make them complicated because that's what makes them more interesting.
As models become more precise and realistic, they also grow larger and more complex. Even with a supercomputer, these calculations take a long time. The solution is artificial intelligence. Instead of using costly quantum methods to predict how atoms move at every moment, a neural network trained on a smaller set of structures can predict their motion.
We are seeing so much more possibilities in the field of computational modeling of materials. We can have models that are thousands times larger. We can run simulations for 1,000 times longer timescales. Yeah, we can see things that we have not seen before.
AI also makes it possible to model more complex structures. Here's an example of a solar cell material with thin layers of perovskite separated by organic linker molecules.
This is a simulation where we take this material and we slowly cool it down from a high temperature to low temperature. And then you see basically how the atoms change their movement, change their behavior. And those details really impact how the device or this material would perform in a device like a solar cell.
One way to make perovskites more stable is to mix different materials together.
So one thing that computations can help with is to identify the perfect mixtures. So this is a bit of a challenge, but we already, I believe, we have the tools, we just have to make it work. so that we can control really which proportion of which element we should use to have the best solar cell material.